Hi guys, welcome back to my channel Pirai Academy. In the series of data structure playlist, today we are going to see about types of trees. In previous video, we already saw about the basic introduction to trees and its terminology. Okay, if you don't saw that video in previously, just go back and watch that video and then come back and watch this video. I will be giving that video's link in the description. Okay, so as you already know from the basics, the tree has a parent-child relation like a family tree. Okay, now first of all, I want you to understand why we are going into new data structures. As I already told you, why we are going from array to the linked list like that. Now, why we are going from the linear to a non-linear data structure. Okay, first of all, we want to know about that so that we can have a clear idea on why I am learning this like that. Okay, fine. So the reason we are going from the linear data structure to non-linear data structure is we want a family tree kind of structure, parent-child relationship. You can see the tree and the linked list are of same structure, but tree differs by a non-linear data structure. Okay, so that's the reason why we are getting into the tree. Okay, at first we are going with the general trees. So general trees don't have any fixed condition, and it is fully flexible. Okay, which means it always be the unidirectional. As you know, trees will be always unidirectional. But what are the flexibility we have? We may have multiple children. That's the one flexibility. The second flexibility is that we don't want the tree to be balanced. In future, I will be telling you what is maybe balanced. Okay, and there are some flexibilities here, right? We don't have any fixed conditions. Okay, so for example, see here, this is the root. Yes, this is a root node, and it has three children. Okay, and these three children have some set of children like that. Okay, here this tree is not balanced. I will be telling you what is maybe balanced in the future, but now just remember it is not balanced. Okay, so it is a simplest form of tree. Okay, now later on we want to search efficiently in the tree. So to search efficiently, what we are going to use in a linear data structure, we are going to use binary search, right? Similarly, whether we can implement this binary search in our tree data structure. If I am going to implement binary search in this tree data structure, what should I do in the structure of the tree? That's going to be the main part, right? So for that only we are getting into binary trees. In binary trees, every node have 0, 1 or 2 childs. Can you understand this? So it is basically like this is a parent have only 2 children, at most 2 children. It may have 1, may have 0, may have 2, but it cannot have more than 2. Can you understand this? So by doing this way, I can tell you that if I want to search any element, I can either go to this way or this way. Can you understand this? So this will be leading to my time complexity by O of log n. Can you understand this? So this is called the binary search, right? So by doing this, we can efficiently search. But here the difficulty is in binary tree, the elements are not in a correct order. In binary tree, if we do a in-order traversal, then the element will be not in a sorted order. So in future, I will be telling you what is meant by in-order traversal. As of now, just know that this binary tree is not suitable to do a searching operation in log n times. Okay, because it is not in a sorted order. As you know, to implement the binary search, we want the elements to be in a sorted order, but here it is not in a sorted order, so I cannot implement binary search. But I attained some conditions like only 2 cases are there. Can you understand this? There won't be more than 2 children. So this is attained. But now My main goal is I want to search. I want the elements to be sorted, right? So for that, we are just getting into the binary search tree. In future, I will be telling the binary search tree. As of now, let us finish all the types of binary trees first. As of now, you understand the binary trees, right? So let us finish all the binary tree types. Then we can go with the binary search tree. My core aim is to make this as a story so that you can understand this clearly. Okay, so be patient. Okay, fine. Okay, binary tree types. So here, what are the types of binary trees we have? So first binary tree is full binary tree. Full binary tree. In the name itself, it is telling what? Full. Full means every node has either 0 or 2 children. Okay, which means in database management system, you will be learning about atomicity, right? So atomicity means either you can do or you don't. Do not be in the between. So it is not big deal. It is not big deal. So it is easy, like you have 0 children or you have 2 children. You cannot have 1 children. Okay. So see here, this is correct. This is the correct form because A has only 2 children, B has 2 children. Meanwhile, D, E and C has 0 children. Okay. So this also correct, but this is a wrong format because B has only 1 children. That's wrong. That's wrong. So these two are correct. Meanwhile, this is wrong. Can you understand this? So this is the full binary tree. If you read the property, you can understand this. So see here. So these properties will be helpful once you are going for a gate preparation. Okay. So this is something important. So be cautious and learn this. Number of nodes is equal to 2 into leaf node minus 1. How? See here. Let us take this binary tree. This binary tree. Okay. So here, number of nodes 1, 2, 3, 4, 5. There are totally 5 nodes. Okay, 5. So which is equal to, so LHS will be 5 and here it is 2 into leaf node minus 1. So how many leaf node are there? 1, 2 and 3. So 2 into 3 minus 1, which is equal to 5. Hence proved. Can I understand this? So always remember, number of nodes will be equal to 2 into leaf node minus 1. Why I am telling 2 into leaf node? Because we know that all the node will have exactly 0 or 2 child. If it is 0 child, it is going to be the leaf node. If it has 2 child, then there will be exactly of 2 into the leaf node, but minus 1 because of the root. Can you understand this? So that's how this is derived. Okay. Number of leaves. So number of leaves is equal to internal node plus 1. So how many leaf are there? There are totally 3 leaf. Okay, 3 is equal to how many internal node are there? Only 2 nodes, A and B, right? Because for this only, I told you want to know about the terminologies so that it will be so simple. Okay. Now, how many internal nodes are there? 2. 2 plus 1. So hence proved. That's it. Okay. Now, number of nodes is equal to 2 into internal plus 1. How it is derived? Derived from this 2. See here, number of node is equal to 2 into leaf minus 1. So leaf is equal to internal node plus 1. So n is equal to 2 into, so what is the leaf? Leaf is internal plus 1. Internal plus 1 minus 1. Can you understand this? Now, number of node is equal to 2i. So 2 here comes 2 minus 1, which is equal to plus 1. That's it. So 2 into internal node plus 1. Can you understand this? So don't want to mark up this. Now, maximum node at height h. So what does mean by height? I already told you that height will be the from the root up to the longest path of the leaf. Okay. For example, here the height will be it will be 0. Here it will be 1 and here it will be 2. So the height of this binary tree is 2 because that's the maximum path, right? Okay, I already just given the definition of height in the terminology itself. Okay, that's the reason why I want you to just watch the terminologies and then continue this. Okay, fine. Now maximum node at height h is equal to 2 power h plus 1 minus 1. Okay, you can apply this and see there. And then minimum height for n nodes. See here, for minimum height for n nodes will be take this equation. So n is equal to 2 power h plus 1 minus 1, right? Now, take this minus 1 to there. So it will be n plus 1 is equal to 2 power h plus 1. Now take a log on both sides. If I take log on both sides, log of base 2, okay, then log of n plus 1, which is equal to h plus 1. Now height will be equal to log of n plus 1 minus 1. Got it, right? Yes, okay. Now maximum leaf at height h will be 2 power h. Okay, so these are the general characteristics or property of full binary tree. Now, what is the use of full binary tree? So it is used in expression matching or expression tree in the compiler design. Okay, and then decision tree. So as you know, decision tree is used in game logics, classification, prediction, and machine learning. Yes. Now Hoffman encoding. So this is the algo that is used in a zip file conversion. Okay, so data compression. There you will be using the Hoffman coding algorithm. For that you will be using this data structure. Okay, then next binary tree is going to be complete binary tree. What is meant by complete binary tree? All levels completely filled except possibly last level. Okay, so this is going to be the complete binary tree. Before that, let us finish the property so that we can understand the above thing. Okay, now levels filled from left to right, which means what? First of all, this is the first level, right? So I will be filling this first level from left to right, like this direction, then this direction, then this direction. So this binary tree is valid binary tree. Can I understand this? So this binary tree is going to be valid. Now here, this is also valid. Here it is not valid because here it is filled. Here also it is filled, but here the D comes here first for this B. For this B child only, this D and E should be there. But here the C having the D and E as a child. So it is invalid, and here it is also invalid. Can I understand this? Okay, so complete binary tree have a property like all the levels should be filling from left to right. Once the level is completed, then only we want to fill in the next level. Can I understand this? Okay, now minimum height of n node is equal to h is equal to log n base 2. Why it is so? Because you can see here, we are filling level by levels. We are filling level by levels. That's the reason why we are having log n base 2. You know, in each and every level, we will be filling of for each and every node, we are filling of two new nodes. So for each and every node, we are cubing with 2 nodes, so that we will be filling like doubling each and everything. We will be filling doubling each and everything. So here comes a floor bracket. This is floor bracket. We want to do a floor operation. Okay. Now maximum number of node for height h is equal to 2 power h plus 1 minus 1. Okay. Now maximum number of node for height h is equal to 2 power h. So these are the general properties of complete binary tree. Okay. Now let us see the uses of the complete binary tree. So see here, the heap implementation is used because of this complete binary tree. So implementation of heap will be using the array, but the imagination part or how we are going to implement this heap will be defined by this complete binary tree. When we are seeing about the heap data structure, the priority queue, we will be seeing this in detail about this complete binary tree. As of now, just understand the complete binary tree property little much. When we are going in depth with the heap implementation, I will be again telling you the complete binary tree. Now, memory efficient and deformed into array. So this is so much important. This is the reason why we are just getting into the heap implementation. Hope you understand up to this. Okay, let us complete here. Let us continue here. So next binary tree type is perfect binary tree. So here all internal node have 2 children and all leaf node will be at same level. Can you understand this? Which means all will be filled. All will be filled. Okay. So see here, this is valid, right? Let me change the color. This is valid, but this is not valid, right? And this is also invalid. I understand this because all the leaf node will be at the same level, but here that's not like that. D, E are different from the leaf level of this C. Here also this D is not in a same level. Can you understand this? Yes. So this is called the perfect binary tree. Now, what are the properties of perfect binary tree? So here the number of nodes is equal to 2 power height plus 1 minus 1. So why? Why we are getting this as the formula? Because as I already told you in the complete binary tree, see here it will be 1 and double it 2 and again double it 4, again double it, then in the next level it will be 8. Can you understand this? So this is called level by level increase, right? So see here 2 power height plus 1. So what is the height of this tree? It is basically 2. It is, see here the height here is 0, here is 1 and here is 2. Can you understand this? Yes. Now 2 power 3 minus 1, which is equal to 7. There are 7 nodes. Can you understand this? Yes. So see here in last level there are 4 nodes. In last level there are 4 nodes, which means leaf is equal to 4. Then the internal node will be leaf minus 1. Can you understand this? Can you understand this? Yes. So that's the reason why I am deriving this formula. So this is similar to the complete binary tree also. Okay. Now number of leaf node will be 2 power height. Yes. Okay. Now number of internal node is equal to number of node minus leaf node. I already told you. So number of nodes. So these total nodes will be equal to internal node plus leaf node. Then what is going to be the internal node? It will be number of node minus leaf node. Yes. And then instead we can also put like 2 power height minus 1. Yes. So derive this and this. Substitute these two so that you can derive this value. Can you understand this? Yes. Now height of the tree, which is equal to log n plus 1 minus 1. How it is derived? So see here, where is number of node? So this. So n is equal to 2 power h plus 1 minus 1, right? Now bring this minus 1 to there. N plus 1 is equal to 2 power h plus 1. Yes. Now take a log of base 2. So here comes log n plus 1, which is equal to h plus 1. So h is equal to log n plus 1 minus 1. That's it. Can you understand this? Okay. So height of the tree is equal to log leaf base 2. How we are getting this? So see here, height and leaf relation. Where is it? So here, take a log on both sides. That's it. Can you understand this? Okay. So this is how we are deriving each and every formulas, and these formulas will be helpful once you are going for a competitive examination. Okay, fine. Now let us see the uses. Here also the uses will be expression tree and the decision tree, as you already saw in the complete binary tree. Okay, now let us get into the balanced binary tree. So listen this carefully. This particular is so much important, because this is going to be the very fundamental part or fundamental unit for the further types of further types of trees. Okay, so balanced binary tree. So here it have some property like height difference of left and right subtree will be at most of 1. What is meant by at most of 1? It may be of 0 or 1. Can you understand this? Yes. So here we can have like height absolute difference for clarification. Okay. So see here, whether this first thing is valid or not. Yes, it is valid. How we are telling that? So see here, first of all, for D, what is the height of D? So what is the height difference of right and left subtree for the D? So here also height is 0, here also 0. So 0 minus 0 is less than 1. Yes, obviously it can be there. Okay. Now here B, for B also. So see here it will be 1 and here it will be 0. So 1 minus 0 will be 1 only. So we may have 1 also, at most 1 only, right? Now let us take for C. For C also, here also 0, here also 0. So it is valid. For A, see here, this left subtree height is 2. This right subtree height is 1. 2 minus 1, which is equal to 1. 1 can be a valid because it is at most 1. So that's the reason why I am telling this as valid. and this is also valid, but this, it is invalid. Can you understand this? This is invalid. And then here, whether it is a valid or not, it is a invalid. Why I am telling this as a invalid? See here, for this C, what is the right subtree height? Right subtree height is 2. Here it is 0. What is the absolute difference? 2. 2. So 2 is greater than 1. So it is violating. So it is not a balanced binary tree. So let us see the properties. So see here, height will be approximately equal to the log n. Okay. So insertion and deletion operation can be done in O of log n. Also searching. Now hope you understand how we are going to optimize the binary tree. Can you understand this? So in binary tree, for searching, it is not suitable for searching. So that's the reason why we are going to BST, the binary search tree. So please be patient and continue with this so that you can understand this clearly. Okay. Now height of left subtree minus height of right subtree, the absolute difference should be always less than or equal to 1. Okay. So these are the two properties of this balanced binary tree. And what are the uses? So it is the fundamental unit of the AVL tree. So this is one of the type. And red black tree, this is also one of the type. And also database indexing. Okay. So database indexing will be like a topic in a database management system. If you already saw that, you can easily recognize the database indexing. Okay. So moreover, the tree data structure will be somewhat useful in the database indexing also. I will be telling those trees. Okay. As of now, just continue with this. Next thing is skewed binary tree. So please try to remember skewed binary tree and balanced binary tree. So these two things will be more helpful once we are getting into the binary search tree. Okay. Listen to this. So skewed binary tree, here node have only one child either in the left or a right. Okay. Which means see here, this is the left skewed tree, this is the right skewed tree. Meanwhile, it is invalid. You can either have left or right. You cannot have left, right, or something like that. Okay. So this is not a value, and this is also not a value because each node have only one child. Here there is second child called D. Okay. Now what is the height? Height will be n minus 1, number of node minus 1, as you know. Then bring this node here, height there. Then node is equal to height plus 1. And the leaf node will be always 1, as you know. Okay. So these are the observation of skew tree. And the uses of skew tree is like, it is used to demonstrate how inefficient a tree is. That's the use. Apart from that, there is nothing. As of now, you understand what is meant by binary tree and what are all the types of binary tree we have. Now in binary tree, what is the disadvantage? The element are not in sorted order. So to avoid that, we are getting into the binary search tree where all the elements are in a sorted order. Okay. So see here, what is in a sorted order means when we are doing a in order traversal, okay, then it should be in a sorted order. That's called a sorted order in a tree. Okay. In future, I will be teaching you what is meant by in order traversal. And also in binary search tree, we have another property. What is that another property is? Always remember, for each and every node, its left child will be always lesser than the node. Meanwhile, the right child will be always greater than the node. This will be followed for each and every node in the binary search tree. For example, see here, let us check the validity of this tree. So 5, whether 5's left child is lesser, yes. 5's right child is greater, yes. Now 2's left child is lesser, yes. 2's right child is greater, yes. Now 9's right child is greater, yes. So this is valid. Now check here, 5 here 2. Okay. So for 5, listen this carefully. This example is pretty much difficult. Okay, pretty much difficult for the beginners. Okay, so just listen this carefully. For 5, 2 is here. Okay, 2 is less than the 5. Now 10 is greater than the 5. Okay. Now for this 2, this 1 is less than the 2, and the 6 is also greater than 2. That's correct. But whether 6 is less than the 5? No, right? See here, observe this carefully. for this 5, whatever its left subtree, this left subtrees should have the lesser value of this 5, but here it has 6, so it is a invalid. It is a invalid. Okay, so whether this is a valid, yes. So what this is called? Skew tree, skew binary search tree. Okay, now let us check here. 10. Okay, for this 10, what is the left child? It is 2. Okay, 2 is valid. 12, it is also valid. Okay, now for this 2, 8 is greater and 9 is also greater, and 8 and 9 are ranges below the 10. So this entire subtree is less than 10 and this entire subtree is greater than 10, and also for each and every node its left subtree and right subtree follows the condition, so it is a valid. Hope you understand, right? Okay, now let us see the properties. In order traversal, when we are doing a in order traversal, we will be getting a sorted order, and then for search, insert and delete, so for these all functionality we will be getting a over h means height. So we already saw that when we are doing a binary search, we will be getting log n as our time complexity. Why here we are getting over h? That's the next thought we have, right? So just see here, this also a valid binary search tree. This Q tree is also a valid binary search tree. Here, if I want to search 1, for example, if I want to search 1, then initially I will be at this 5. Okay, 1 is less than 5, so I will be going here. 1 is again less than 4. Again, I will be going to the left side. Again, I am going to the left side. Again, I will be going to the left side. So here, I traversed all the nodes. Here, the time complexity will be O of n. So now, I remember the disadvantage is we want all the nodes should be in a balanced condition. If it is not in a balanced condition, if it is a skew tree, then it is inefficient to search, insert, delete. Can you understand this? Okay, so that's the reason why we are going from binary search tree to AVL tree. Okay, so before that, let us finish this minimum element. What is the minimum element? Minimum element will be always the leftmost element. See here 1 is the minimum element. Here also 1 is the minimum element. Here 2 is the minimum element. So this 2 is the leftmost element. Other things are right side. 8 is a right element and 9 is also right element. So 2 is the leftmost element. Don't confuse this. Okay. Now, rightmost element will be the maximum. So these two properties will be more important when we are going for the problem solving. There they will be asking you to find the leftmost element and the the maximum element and the minimum element in a balanced binary search tree. In a time complexity of O of log n, there it will be much useful. Okay. Now see here, what are the uses? Uses are searching, inserting and deleting, foundation of AVL and red black tree, and database indexing. So these three are the main uses of this binary search tree. So as I already told you, what is the disadvantage of binary search tree? It is not in a balanced way, so that the time complexity is inefficient. To avoid that, we are going with the AVL tree. Now hope you understand why this AVL tree data structure is coming into the role. Okay, so the basic definition is self-balancing binary search tree. So in this video, you don't want to understand how it is going to balance it, but understand that it will be balancing somewhat the binary search tree. It won't let the binary search tree to be unbalanced. Okay, so see here whether this is a valid thing or not. Let us check whether this is a valid binary search tree first. Yes, it is a valid binary search tree. Okay, so before that, let us finish the property so that you can understand, right? I know what it means, but you want to understand, right? So let us understand this and you answer what are those correct and what are those invalid. Okay, hereafter we will be doing like that. Okay, so height difference of left subtree and right subtree is at most 1. So this is one of the property of BST, binary search tree, and this is also the property of binary search tree, and this also a property of binary search tree. Yes, and then here insertion, searching, deletion is optimized than the binary search tree, so that here comes the O of log n. Meanwhile, there it will be O of h, the height. And then in order traversal, it will be also giving a sorted order. So this is also similar to the binary search tree. Okay, the only difference is it is balanced. It is balanced. Okay, so now tell me which trees are valid and which trees are invalid. Okay, pause here and check. Just go through. I will be continuing it. Okay, fine. So see here. Here is 5. So its left child is lesser than it, and its right child is greater than it. For the right child also, its left child is lesser and its right child is greater. So both the subtree for 5, this entire subtree is greater and this entire subtree is lesser. And for 10 also, this subtree is lesser and this subtree is greater. So I can tell that it is a valid binary search tree. Now I want to check whether it is a balanced or not, right? Okay, let us check with the 5. What is the height of the left subtree? It is 1. It is 1. What is the height of the right subtree? It is 2. So 5 is balanced. Now what is the height of the 4? So subtree, 4's left subtree, 0. Here also 0. So it is valid. Okay. Now, yes. Okay. Now come to 10. So here also 1, here also 1, valid. Here 0, here 0, valid. Here 0, here 0, valid. So it is valid. Yes. Okay. Now let us get into this. So here 5. Okay. Here 3. Okay. So here 12. So it is greater, and 13 is greater, and 6 is less than 13. Okay. So perfectly a binary search tree. Now it's time to check whether it is a balanced or not. Okay. Check. So whether it's a balance for 5, here it is 1, but here it is how many? 1, 2, 3. 3. Whether it is valid. Whether it is valid? No. No. So it is not a AVL tree. It is not a AVL tree, but it is a binary search tree. Okay. Now let's check here. So whether 5 has a lesser value in its left subtree? Yes. Whether 5 has all the greater value in the right subtree? No. 4 is less than 5, but it is lies in the right subtree. So it is not a AVL tree as well as not a binary search tree. Can you understand this? Okay. So these are the properties of AVL tree. As of now, you don't want to understand how we are going to balance it. Just understand it is also one of the kind of tree that makes the disadvantage of binary search tree into an advantage. Okay, fine. So as you know, it is useful in searching, database indexing, and memory allocation and file management. Okay, fine. Now let us get into the another self-balancing binary search tree called red-black tree. Okay, so this red-black tree will be the inbuilt library trees. Like in Java, you will be having a tree map, right? So in the tree map, they will be implemented using the red-black tree. So red-black tree is like it have 2 colors of every nodes. Either it is red or it is black. So that's going to the first property. So see here, node colors either be red or black. Okay. Now root and leaf will be black. Compulsorily should be black. If the node is red, then its child will be black. Understand the difference. If the node is red, its child should be black. It is not necessary. If the parent is black, its child should be not black. It may be black. Can you understand this? Next, this is going to be very important property. For each node, every path to leaf node has the same number of black node from each node. So yes, from each node, every path to the leaf node has the same number of black node. So this is going to be much more important property. So see here, next thing is rest of them will be same as the binary search tree. Okay, so we have seen all the properties of the red-black tree, right? Now I want you to tell me which one is valid and which one is not valid. So let us check this first, the first thing. So let us check this. Okay, now the first condition is the root node and the leaf node always should be black. So here the leaf means these things. So these things will be marked as a nil. Okay, and remember, this is how the red black tree will be. At last there will be a nil node that will be of black color, and see here, every leaf node are black and root is also black. Okay, so it is valid. So we have finished the first condition. Okay, what, sorry, here the first condition, and here the all the node will be having a color of red or black. That's also valid. Now if the node is red, then its child will be a black. Okay, so see here, here is red, so its child is black. Here is red, its child is black. Here is red, its child is black, and here is red and its child is black. So I can tell from this slide it is also valid. Okay, so let me mark here as valid. Now for each node, every path to the leaf node has the same number of black nodes. So here we may have a bit confusion what this statement means. So see here, I am starting from this root, for example. So let me take this path, this path. Okay, so in this path, how many black nodes are there? One is this 2, then next thing is this nil node. So in this path, it have a black node of two black nodes, right? Now follow the green path. So if I go like this, now tell me how many path I have. Sorry, how many black node I have? One is this 2, another one is this nil node. So here also you have 2 black nodes. Yes. Now follow the orange path. So now I will be going from 10 to 5, then 7, and then this node. Okay. Here also I will be having 7 and it's nil. So here also it will be having 2. Like that, you can see all the paths of each and every nodes. They will be having similarly like these numbers. Can you understand this? So this is the reason why we are checking for this condition. Now hope you understand what this condition means. If you still cannot understand this, okay, while we are implementing the red black tree, you can understand this clearly. Okay, now rest of the property will be same as the BST. So let us check for the BST. So for 10, all its left subtree is lesser value and all its right subtree is greater value. And for this 5, all its left subtree is lesser and right subtree is greater. Meanwhile, all the nodes are following the BST condition, and also whether it is a balanced tree. Yes, it is a balanced tree. Can you understand this? Yes, you can observe this. It is a balanced, right? Okay. Now see here, see in this second example. In the second example, you can see here 2 red nodes are consecutive. So here itself you can tell that it is a not valid red black tree. Can you understand this? So red black tree is like difficult to understand, but if you understand this, you can easily implement the red black tree. Okay, after the red black tree, when we are going for the database concepts, like the disk management, in the disk management, we will be having a inefficiency in a red black tree. So we are getting into the B tree. Can you understand this? So this is how we are getting into the new data structure called B tree, especially for the disk management. Okay, so here we can tell this as self-balancing M-way tree. What it means? Self-balancing M-way tree. Here you will be having something like order. Okay, so what are the properties of this? So first of all, the property is it should be balanced. Okay, and the next property is each node have multiple keys and data with respect to the order. Okay, for example, if the order is 4, let me write here, if the order is equal to 4, then it have how many keys? It have 4 keys and data will be of 3 data. Can you understand this? Okay, so let me give you the example so that you can understand this clearly. Okay, so see here, this is called a B tree. Now this B tree is both of searching, will be having a both of binary search tree property and also a balanced property. So here it is not a binary search tree. Here it is a m ordered search tree. We may have multiple order. Okay, so see this, observe this carefully. First of all, I am having order of 4, right? So we have 4 4 keys. So this one is first key, and this is second key, and this is third key, and this is fourth key. Understand this clearly? Yes. Now here I am having 6 and 10, right? So here I have a linkage. This is a key. Here I will be having what are those values which are less than 6. What are those values which are less than 6? Here in this key I will be having what are those values that are greater than 6 but less than 10. And then here I will be having what are those values that are greater than 10. Okay, as of now, know about the B tree. You don't want to understand how we are going to construct this. Okay, my core intention on this video is you want to have some basic foundation so that we can step into the each and every types of trees. Okay, now here also we have 4 keys and 3 data. Okay, so here we will be having less than 3, the elements which are less than 3. Here you will be having elements that are greater than 3. Here you will be having elements that are less than 8. Here you will be having elements that are greater than 8. Okay, here you will be having elements that are less than 12. Here you will be having elements that are in between 12 and 14. Here you will be having elements of greater than 14. Can you understand this? So because of this, we can easily go and access and retrieve the data in a disk memory. As you know, we are just getting into the database. In database, we have millions of data. In those millions of data, by splitting them into like this, some order, it will be more efficient than splitting it into a binary format. Okay, which means splitting into 2 is way inefficient than splitting into more than 2. Can you understand this? So that's the purpose we are introducing the B tree. Okay, and see here what are the uses of B tree. Here it is used in the old database only. We know about the advantages of the B tree. We don't know about the disadvantages of the B tree, right? So in B tree we have some of the disadvantages, like we cannot access the data in a sequential order. Okay, so which means we want to traverse, like I am at this point. Okay, I have traversed up to this. Again, if I come back to next to this leaf, then I want to go back and come here. Okay, when we are taking the traversal, when I am teaching you the in order, pre-order, post-order traversal, you can understand what is the inefficiency in the B tree. You can you will be traversing this using DFS traversal, right? In that time you will be going like this and then coming here to go to this particular leaf. Instead of this, in B plus tree we can go in a sequential order because all the leaf nodes are connected and all the data will be there in the leaf node. That's the difference between B tree and B plus tree. Now let us finish the uses of B tree. See here, disk accessing and searching, file management, database indexing, and memory management. So these are the uses of B tree. Now let us get into the B plus tree. As you already know, in B tree all the leaves are not linked or connected. In B plus tree all the leaves are linked, so that we can easily search in a sequential order, and also B plus tree is efficient than the B tree. Now hope you understand why we are going from B tree to B plus tree. Okay, in B plus tree the property are balanced. Each node have multiple keys and data. As you know, if the order is 4, then it have 4 keys and 3 data. These are similar to B3 and B plus 3. The only difference is all leaf node are linked. This makes us to go sequential order. Okay, now have redundant key. What is we made redundant? Duplicate. So see here, by seeing this example you can understand. So see here, 7. So 4 is less than 7. Again, you don't want to understand the implementation. Just understand what does this diagram mean. Okay, now here all the elements that are less than 4. Here all the elements that are greater than 4, but 4 is also there. Can you understand this? Yes. So here 7 is also there, but 7 is here or also here. So that's the reason why I am telling you all the data will be at the leaf node. That's the reason why we are having a duplicates. Okay, so by making this as a linked, we can go and search in a sequential also instead of going again to the top and going to the leaf. Okay, so this makes us the searching faster and efficient. Okay, what is the uses? It is used in the modern database like Oracle. Okay, and this also have the same uses as the B tree, but it is more efficient. Okay, so we are getting into the last tree type. So as of now we have everything. So every tree types are completed. The last tree type is trace. Why we are getting into this data structure? Because the trace are more focusing on the strings. For example, the real-time application is, see here, you have used the search engines where when you are typing some values, or sorry, when you are typing some characters, okay, the search engine will be generating automatically some of the suggestions. Those suggestions are because of this trace. Okay, in Google also they have using the trace. This trace is also called as a prefix tree or digital tree. So the basic understanding of trace is prefix or digital tree used to store dynamic string efficiently. When I am telling you what is meant by trace, in following example you can understand how it is used in the search engine prediction. Okay, fine. So what are the characteristics? So each node represent a character. Okay, root to leaf make a word or build a word. Okay, root will be empty always, and multiple childrens up to 26. You may also have more than this, because nowadays the search engines also have the something like special characters also included, right? So it may be varies upon your application. Okay, as of now just remember this alone, multiple childrens. It is not fixed like it only have 2 children, it have multiple children. Okay, so see here, this is the trace. Root will be empty. This has to implement the empty, implies the empty. Okay, now it has 3 children. Okay, so it is not it is not condition like we only have 2 children or 3 children or 1 children. You may have any number of children. Okay, so see here, BALL, ball. So this is one of the word. Okay, next go here, BAT, bat, BE, B, CAT, RAT. Now hope you understand what is the use of trace. So this is how it will be easily predicting what you are going to search. For example, this is the simple trace, right? In actual, the trace will be so much huge. As of now, let me take this alone. Okay, now for example, you are typing the B, then what are the possible words you can fill there? So ALL maybe one of the option, or AT one of the option, or E one of the option. Now if you go with this A, then this will be disappeared and you will be having LL and T alone. Can I understand? Yes. So this is the use of the trace. So if you want to learn more about the trace, then you can go and solve the LeetCode problem called word searcher, I think. Word searcher 2. Here you are going to implement this trace in terms of competitive programming. Okay, so it is much difficult, but still if you learn this, it will be so much easy. Okay, and it is more useful also. Now let us see the uses. So first use is autocomplete or predictive test. So this is what they will be using in a search engines, right? And then spell checkers, and also text processing and search engines. There also it will be useful. So that's all about all the types of trees, and Thanks for your patience for watching all the types, because many people don't have patience to watch all the types of trees. And congratulations, you have gone with this much video, and now you have headed to this part. Okay, and this much the pretty much of all the types in the trees. And in upcoming videos I will be implementing each and every types of trees. Okay, and if you really like this video, and subscribe to my channel. Don't skip any videos in this playlist, because all videos will be helpful once you are going with the competitive programming or GATE examination. And if you have any doubts regarding this, then you can just comment below. I'll be answering in the comment, or I'll be giving you a separate video also. And if you have found out any mistakes, you can just tell in the comment section. I will be rectifying the mistake in upcoming future. Okay, thank you.